So let's talk about what happens if you already have one of the ions in solution. So if we have one of the ions already in solution, we have what we call a common ion. So for example, if we have magnesium fluoride and we were trying to dissolve it in a solution of calcium fluoride, well, there's already fluoride ions present. So that's going to reduce how many of the fluoride ions can dissolve from the magnesium fluoride, which means that we're going to reduce how much of the magnesium fluoride can dissolve, because we've already got fluoride ions in solution from the calcium fluoride. So if we try to dissolve something when we already contain one of the ions, we're going to reduce the solubility of that solid. So let's take an example where we want to calculate the molar solubility of magnesium fluoride and 0.10 molar sodium fluoride at 25 degrees Celsius. Now, let's think back a few slides ago, where we calculated the molar solubility of magnesium fluoride. So we came up with 2.64 times 10 to the negative 4th molar. So I'm going to write that value up here. And we're going to compare that to what the molar solubility of magnesium fluoride is in 0.10 molar sodium fluoride. So if we have sodium fluoride in solution, that's going to give us sodium ions and fluorine ions. So, if our concentration of sodium fluoride was 0.10, our concentration of fluoride ions is going to be 0.10. So, when we try to dissolve the magnesium fluoride in there, we only get one magnesium ion, so we can represent that as X. Now, the concentration of the fluoride ion would be 2 times whatever that magnesium concentration is, but we already have 0.10 molar in there from the sodium fluoride. So our concentration of fluorine at equilibrium is actually going to be 0.10 plus 2x. So let's try to work this out and look at the difference in the molar solubility when we try to dissolve magnesium fluoride in water versus magnesium fluoride in 0.10 molar sodium fluoride. So KSP, the expression isn't going to change. So we have magnesium, concentration of magnesium times the concentration of fluorine squared. So we have 7.4 times 10 to the negative 11th is going to be equal to X times the concentration of fluorine squared. Now, if we try to multiply this out, square this expression, and then we multiply x in it, this is going to get really messy. Because what's going to happen is we're going to get an x squared here, plus x, plus some constant, because this is going to be a quadratic equation here. But then we have to multiply this x in here, so we're going to end up with x cubed and x squared. So that's going to get a whole lot of math to deal with that we don't want to have to deal with. So we're going to make our lives a lot simpler. And we're just going to assume that this expression is small enough, that 2x is small enough, that we can just assume that it's 0. So that will be the way that we approach these types of problems. And if you were to go through and do the math, you would find out x does come out incredibly small, so we can assume that this is negligible. So we have 7.4 times 10 to the negative 11th. So we just have 0.10 times x, but this 0.10 is squared. So we're going to have x times 0.10 squared, and then we're going to divide both sides by 0.10 squared. So we get that x is equal to 7.4 times 10 to the negative 11. Divide that by 0.10 squared, which comes out to 7.4 times 10 to the negative 9th molar. So look at the difference between the solubility in water and the solubility in sodium fluoride. So we have 2.64 times 10 to the negative 4th. We have 7.4 times 10 to the negative 9th when we're in sodium fluoride. So a factor of 10 to the negative 5th, or 10 to the 5th here, is the difference in solubility. So we have a much lower solubility when we're trying to dissolve our magnesium fluoride in something that has a common ion. Which would make sense because there's only so much of any given ion that will dissolve in water. And if we've already got some of the fluoride in there, then that's going to limit how much more we can put in there when we try to add our magnesium fluoride. So this is what we were just calculating here, that we have a difference of 10 to the 5th here when we try to dissolve our magnesium fluoride in something that has a common ion. So think about Le Chatelier's principle. If you've already got fluoride in here, you're essentially adding more fluoride, so you're going to drive the equilibrium back in the other direction. So we can see if we try to increase the concentration of fluoride ions, as we do that, the solubility of magnesium fluoride decreases. So let's take a look at another example here. We have calcium fluoride, and we want to dissolve that in a 0.25 molar sodium fluoride solution. So if we dissolve calcium fluoride in solution, we get calcium ions and fluorine ions. So at equilibrium, we're going to have some concentration of calcium ions. Since there's already 0.025 molar sodium fluoride, which means that we have 0.025 molar fluorine, then our concentration of fluorine is going to be 0.025 plus 2x. So we can write our KSP expression for this. So we have a KSP of 4.0 times 10 to the negative 11. So we can plug in X for calcium and 0.025 plus 2x squared for fluorine. And again, to make our lives a little bit simpler, we're going to assume this 2x is small enough that we can ignore it. So we get and then we're going to divide by both sides. So we get x is equal to 4.0 times 10 to the negative 11th. Divide that by 0.025 squared. And if you plug that into your calculator, you should come up with 6.4 times 10 to the negative 8th molar. Now we can also use this idea of forcing equilibrium in one direction with pH. So for example, if we take something that's not very soluble and we dissolve it in an acidic solution, sometimes we can actually increase the solubility. So for certain compounds, and particularly for a lot of ionic compounds, if we put them in an acidic solution, if they're not very soluble in water, we can increase the solubility. So what happens here is we would get, if we just did calcium in water, we would get calcium ions and carbonate ions. Well, what happens is when we have this in an acidic solution, we have a proton that can combine with this carbonate ion, which reduces the negative charge on it, and then we get water. So this drives the equilibrium to the right because we form these bicarbonate ions instead of just the carbonate ion. So if we increase the pH, we're going to decrease solubility. So for increasing pH, this would be in basic solution. So we would go back towards the reactants. If we decrease the pH, meaning we're in acidic solution, we would increase the solubility and we shift the equilibrium toward the right, towards the products. Now, just like with our equilibrium constants, we can also calculate a value for Q, which was at any point. We can do the same thing with KSP. So KSP is only at equilibrium, but we can also calculate an ion product, which we represent as QC, and we can use that to determine if our reaction is at equilibrium. So let's look at some examples where we have to calculate Q and determine if we're at equilibrium or which direction we would go. So before we do that, let's look a little bit more at specific cases. So if Q is greater than KSP, that means our solution is supersaturated. It has more of the compound than it can hold, and so some of the compound is going to precipitate out as a solid. If Q equals KSP, our solution is saturated and we're at equilibrium. So KSP is our equilibrium constant, which means if Q is equal to that, we're already at equilibrium. If Q is less than KSP, then the solution is unsaturated, meaning we're not at saturation, we're not at equilibrium yet. So none of the compound is going to precipitate out. And we could even add more if we wanted to. We don't necessarily have to. Sometimes we may not want to get to the level of being saturated. We may want a solution of lower concentration, but if Q is less than KSP, then none of our compound is going to precipitate out. Okay, so let's look at an example where we calculate Q and determine if a compound will precipitate out. So we're going to mix 275 milliliters of this concentration of lead nitrate and 125 milliliters of 0.339 molar sodium chloride. And we want to know if lead chloride will precipitate out. So we're giving KSP for lead chloride. So if we have lead chloride in solution, or if we had lead chloride and wanted to dissolve it, the equilibrium would be lead 2 positive plus 2 chlorines. So we write Q exactly the same way we write KSP. So Q would be equal to lead 2 positive times the concentration of chlorine squared. So remember, KSP is the equilibrium, Q is at any point. So we're going to get the lead from the lead nitrate, and we're going to get the chlorine from the sodium chloride. So we need to calculate the concentration of lead and the concentration of chlorine that's going to be in our solution when we mix these two solutions together. So we have 275 milliliters and 125 milliliters that we're going to mix together, which gives us 400 milliliters, or 0.4 liters. So we're going to go through and we're going to calculate the concentration of lead, and then we'll go through and calculate the concentration of chlorine. So we have 275 milliliters of 0.134 molar lead nitrate. So 275 milliliters would equal 0.275 liters. So we have 0.275 liters of 0.134 molar, which means 0.134 moles per 1 liter. So 0.275 times 0.134 would give us 0.03685 moles. And I'm purposely going out a few extra decimal places since we have a few more calculations to do here. So if we divide that by the 0.4 liters of total solution, you take the 0.3685, or what would be better is just to leave this calculation in your calculator and then just hit the divide by 0.4 so that you divide by the original number you came up here and not the rounded answer. So take this answer divided by 0.4 and you should come up with 0.09213 molar lead. And then for sodium chloride, we have 125 milliliters of 0.0039 molar. So 125 milliliters converts to 0.125 liters. So we have 0.0339 moles per 1 liter. So if we multiply that out, we get 0.00423. 75 moles. And we're going to divide that by the 0.4 liters to get the concentration. So if we divide that out, we get 0.01059 molar for the chlorine ion. So now that we have the concentration of lead and chlorine, we can plug that into our expression for Q and determine whether we're at equilibrium or not. So I'm going to do that on the next slide here. So we said Q is equal to the concentration of lead times the concentration of chlorine squared. So we take 0.09213 times 0.01059 squared. And if we multiply that out, we get 1.03 times 10 to the negative fifth. So if we go back to the previous slide, we wanted to know if lead chloride would precipitate out. And the KSP for lead chloride is 1.6 times 10 to the negative fifth. So that's our Q. And KSP is equal to so the question is Q greater than or less than KSP? Well, 1.03 times 10 to the negative fifth is slightly less, not by too much, but it's less than 1.6 times 10 to the negative fifth. So Q is less than KSP, which means that lead chloride will not precipitate out. Let's take another example here. Will calcium fluoride precipitate when 150 milliliters of calcium chloride and 100 milliliters of 0.20 molar sodium fluoride are mixed? And we have KSP for calcium fluoride. So again, the calcium for calcium fluoride is going to come from the 0.10 molar calcium chloride, and the fluoride is going to come from the 0.20 molar sodium fluoride. So I'm going to go ahead and add another slide here. Okay, so I run out of room here. So if we write the equilibrium expression for calcium fluoride, so calcium fluoride would give us calcium and the fluorine ion, or fluoride ion, I should say. So we need to calculate the concentration of calcium and the concentration of fluorine, and then we can go ahead and write our expression for Q. So if we take the 150 milliliters of 0.10 molar calcium chloride, so we're going to add 150 milliliters and 100 milliliters of solution together, which is going to give us 250 milliliters of solution. So if we have 150 milliliters, that's 0.150 liters, and we're going to have 0.10 moles per liter, since we have a 0.10 molar solution. So if we take 0.15 times 0.10, we get 0.015 moles of calcium. And we are dissolving that in a 0.25 molar solution, or we will have, a 0.25 liter solution. So we'll have 0.25 liters of solution when we mix these together. So 0.015 divided by 0.25, we get 0.06 molar for the calcium. And then for our sodium fluoride, we have 100 milliliters, which is 0.1 liters. So if we take 0.1 times 0.2, we come up with 0.02. moles. So if we take 0.2 divided by 2.250, we get 0.08 molar for the fluoride ion. So we can plug our concentrations of calcium and fluoride in. So we have 0.06 times 0.08 squared, and that gives us 3.8 get this in the same color here. 3.8 times 10 to the negative 4th for our value for Q. So if we compare that to our value for KSP, 3.8 times 10 to the negative 4th is greater than 1.5 times 10 to the negative 10th. So Q is greater than KSP, which means that calcium fluoride will precipitate. Okay, so this is another example here, and I'll let you work that one out on your own, and we will get some more practice with these examples in class. So sometimes we can selectively cause something to precipitate out by adding certain ions. So for example, if we want the metal ion to precipitate out, and the anion will react with acid and give us the protonegative version and water, then we can dissolve our metal with our anion in an aqueous solution and we can get the metal out. So sometimes we can force something to precipitate out if we want it to, by just adding something that will cause it to precipitate out. And we can actually use this idea if we compare QC to KSPA, which is our solubility product in acid. Then we can determine if we change the pH, if we're able to force the metal to precipitate out. So we can actually use this when we do things like this sometimes in lab, where you might have an unknown solution and then you add different things to your solution to see what you have. So for example, if you had hydrochloric acid and something precipitates out, you know it has to be one of those ions. And then if that didn't work, you'd add a different acid, or you might add a base, or you might add an ionic compound to see how those things react. So it's called qualitative analysis, where we take an unknown solution and then we try adding different things and see what our reaction is. And that leads us to an answer as to what we have. So we will stop here and we'll get some more practice with KSP and calculating KSP and QC in class. So I will see you in class.